So recall a strophoid that we've covered on previous videos. It's basically defined by a point N called the node, a point F called the focus, and a line that passes through N. We're calling this line K, and we're going to call this line the asymptote because the curve becomes tangent or becomes parallel to the asymptote as it goes toward infinity, right? Okay, now let's remember how this thing is built. I place a point P of t anywhere on the asymptote. Then I draw a circle that is centered on P of t and passes through N, the node. And then I just compute the two intersections S1 and S2 of this circle with a line drawn from P of t to the fixed point F. Okay, so as I slide P around, I sweep, these two intersections sweep the strophoid. Okay, and I can change, all my parameters here, etc., etc. The strophoid becomes symmetric, right? It's a right strophoid when NF is perpendicular to the asymptote, but that's besides the point. This video is about is a generalization of K, okay, and what that entails. So one thing we can say here is we cannot compute the area of this curve. The area of this curve is infinity because, the strophoid is extending to infinity on both sides. But what if K was actually this particular asymptote here? Straight line is a degenerate case of a more general case where K is a circle, and in this case here, the circle has infinite radius. So let's look at this case. Here we have, I've made K be a circle, and I'm going to use the same construction. I'm going to move a point P of t through my now non-linear, okay, or non-straight line, asymptote, quote unquote. This is no longer an asymptote, but this is just a circular base curve here for P of t. And I'm going to do the same thing. I'm going to draw a circle that passes through N, and then compute the two intersections, S1 and S2, of this construction circle with a line from P to F. Okay? So as P sweeps, I get this interesting shape here, this interesting curve. Okay? So let's remove the construction, and let's just show that I can move F around. Okay? F can be outside. F can be inside K, in which case I get this other topology, okay? And F can also be on K, in which case I get an even simpler topology, which is basically two circles, two intersecting circles. It turns out that the sum of the areas of these two circles is constant, okay? But we're going to see an even more general picture of this in the next simulation. All right? So let's go ahead and detach F. You can see here that you go through all these interesting curves. Okay, we haven't analyzed their topology very much, but you have these two regimes. You have this outside regime and this inside regime. Okay, all right. Let's go to the next simulation. So here we're going to talk about the exact same construction. Namely, I have a circular K. In this case, I just made K equals the radius of K equals to 1 without loss of generality. Okay, and then I have the same idea, right? I have a circle that is traveling along K. I'm drawing a construction circle centered on P of t that passes through N, and then my curve, as before, is given by the two intersections S1 and S2 of this construction circle with a line from P to F. Okay, so you get this strophoid. Now, what we want to talk about here are F-isocurves of strophoidal signed area. Okay, so for example, what happens to the area of this curve as I move? Let me reduce the number of samples here. As I move F around, so I'm moving F around. I'm watching the area of this curve. In fact, I'm computing this area here numerically. You can see this number here is a numeric area, right? So I can see that I'm at 2.0, blah, blah, blah. So the question we asked was, what were isocurves of F such that the area of the strophoidal curve remained constant? And what Ronaldo Garcia helped me derive was that, surprisingly, you got two regimes, as we saw before. If F is outside K, okay, the isocurves of area are, let's see here, if F is not in K, so it's outside, The isocurves of area are circular arcs whose with a diameter line on NO or ON. So you can see here that this is the first one, this is the second one, and that these are circular arcs that they have endpoints on K, but they pass through O. They pass through O, the center of K. Correct? So let's go ahead and try to test that. I'm going to go ahead and attach F to this locus here. Let's see if it lets me do it. Okay, let me do it. So what we're saying is that if F moves along this circular arc, the area of the red strophoidal curve does not change. Now, how am I actually getting, and in fact it's equal to pi. So this is the A equals pi isocurve. We picked a particular isocurve here for which A equals pi. And what I'm doing here is I'm showing a numerically calculated area on the left. And how am I numerically calculating this area? I'm basically sampling my construction on n different locations, say at even angles around K. And for each one of each such location, I get a point on the curve. And then I just consider this curve as being a polygonal, approximated by a polygon with many sides, in this case 60, and I compute its signed area. Okay, so I'm computing the area of a polygon here, but we actually have closed form solutions. I'm doing this numerically here for 60 samples. So you can see here that my result is close to pi, but it's not equal to pi. Well, it's going to get closer to pi if I increase the number of samples, say to 360, for example. So let's take it to 360. So now I'm saying, okay, it's 3.141, blah, blah, blah. So yes, we have worked out that this curve here, you can see here on the left, as I move F on this isocurve, my area is around pi, okay? What if I go to this other isocurve here, where Ronaldo tells me that the area is equal to 4. So let's go over there. Okay. Okay, so I place it over there. So I can see here on the left that my area is pretty close to 4, right? And I can move F around this arc of a circle, and I can watch on the area on the left and see that it's not changing much. Okay, so this is the first observation. Namely, let's detach that the F-isocurves of area, okay, when F is outside of this base curve K, are circular arcs, okay, whose one diameter is aligned with NO, okay, and that pass through O with endpoints on K itself. Okay, so that's the first statement. Now, as we saw before, something weird happens, and let's reduce the number of samples here so that I get a faster simulation, because this is being done numerically in GeoGebra. So we saw that there is this topological change when we do this, right? But before we undergo the topological change, let's go ahead and place F on the circle K. Okay, right there. So we saw before that when we do this, we get the union of two circles, and I kind of mentioned that the sum of their areas, or their total area, was equal to, was constant. Well, Ronaldo actually gave me a number for that. It's actually equal to 4 pi. Okay, so you get 4 pi, you're saying 3.14 times 4, you're going to get something like 12.4 or something. Okay, let's increase the sampling here to see if it improves. Yeah, let's go to 360 samples. Yeah, I'm getting something like 12.55. What is 4 pi? 4 times pi, that's 12.566 something. So I'm getting, yeah, I'm pretty close, right? It should be 12.56, and it's 12.55. That's because I have 360 samples, okay? But the key thing here being that as F moves, I'm getting these two circles. Both of them pass through the node and through F. That they are thus specified. Okay, so an interesting thing might be, okay, let's figure out, are there their centers are going to be on, both centers seem to be on K itself, right, just by eyeballing it, but that's besides the point. Let's go to the next zone of interest here, which is when F is inside when F is inside K. So let's put it there. So now we get this other topology. We got these two internal lobes, right, if you will. Okay, you can see here. Now, what we noticed was that the isocurves here, now they degenerate to straight line chords of K, which are perpendicular to NO. So for example, if I place F on this first chord here, okay, for example there, my area becomes exactly 23. And if F is moved along this isocurve of area, the area doesn't change. Okay, if I go to that bottom one there, let's go ahead and take that other one, attach, detach. So let's put it there. Let's put it here. Okay, so what if I move here? Okay, we've predicted that this is going to be 18.8. This is probably some interesting number. It could be irrational, but it could be, you know, related to pi somehow. I would have to look back on my notes. But the key point being that here that if you're inside K, if F is inside K, and you're seeing here on the left that my area is not moving much, let's make it be 360 samples again, just to double check. So you can see here that the area is about 18.8. Okay, so we're getting something interesting. And what is this formula? It doesn't matter much, but the key thing being that when F is inside of K, my isocurves of area are chords that are perpendicular to NO. All right. Anything else here? Yeah. So my isocurves of area, okay, for F being outside, are really a pencil of circles, which all pass by O. Here's another member of the circle. It's going underneath. Okay. So I have a so-called parabolic pencil of circles. You know, they're all arcs. They're circular arcs that belong to a pencil of circles. And they're called parabolic because they have a single point of contact here, common, right? Okay, so this is observation, say, 2. Now let's move on to another kind of generalization. If you go back to our, you know, regular strophoid, right? Recall that the asymptote passes through N, and then on our second construction, we also made this circular generalization of the asymptote pass through N. Now let's look at a case now where this circular locus of P of t does not pass through N. In fact, we're going to make N be the center of this locus. Okay? We always try to like break symmetry in small steps, right? So that we preserve some structure to the problem. So that's the case here. So now, same idea, making P of t move along a base circle K, okay? And always making a circle centered on P of t pass through node N, and then I compute the two intersections S1 and S2 to trace the curve. Okay, so this guy has even more interesting area consequences in terms of F, right? So they're actually listed on the left here. If F is outside of K, it doesn't matter where F is, the area is always 2 pi. The area is wherever F is. F can be really far away, the area will be 2 pi. How do I know it's 2 pi numerically? You can see it's already pretty close. Let's go ahead and put this at 180. Yeah, it's getting closer to 2 pi. So it doesn't matter where F is, you get area 2 pi. That's kind of cool. Now, if F is inside, you get signed area equal to 4 pi, regardless of where F is. Okay, now I think that for this area to have units, I made the circle have radius 1. Okay, so this is for radius, K radius equal to 1. Now what if F is on the circle? Okay, let's put it there. Okay, so you get this interesting curve. This could be a limmason of Pascal of sorts. Okay, we'll have to derive it, but I think we've already got its closed form. But the interesting thing is we're getting 3 pi. So it's as if we have 3 regions. We have a 4 pi region outside. We have a 4 pi region inside. And then we have this singular region, 3 pi. There's nothing in between. The area solutions are discrete. Why is that? Because there's a change in topology, right? That is unsmooth. So for example, as I'm approaching F to the circle, I'm going to undergo an inversion of sorts, right? I go through that two-circle solution, and I come back in, right? So this continuous topological change, okay? I said two circles. There are no two circles here. This is always, you go through this limaçon, right? Makes sure that there are abrupt transitions in area, okay? So this is pretty cool. Last example in this video, breaking the geometry one step further. So now I'm going to continue to have a circle K where P of T, okay, so here I don't have that. I don't have that thing. Okay, that's fine. I don't have an option to show the construction, but assume it's the same construction, okay? I have a point riding, a P of T riding on K, and then I'm going to, now the difference is that my node is not on the circle K as it was before. It's outside, okay? So what's going to happen here? I'm going to continue to get isocurves of F, which are when F is outside. So it says here, when F is outside, there's still circular arcs, okay, whose diameter is along NO, okay, and that continue to pass through not C but through O. Let me change that through O. Okay. Yeah. So you can see here that this is one isocurve. Let's test that. Let's test that. So how am I going to do that? Well, when F is on K, you also get kind of like a constant area. So this is an isocurve itself. You can see here that when F is outside, let's go ahead and place it over there, attach F to this isocurve, and then the interesting thing in this example is that you're getting two disjoint curves, okay? But let's increase to 180. We might have picked the area here to be -1. We picked a particular isocurve such that the area is -1. Let's increase the number of samples here. It could be, okay? I'm just looking at this number. I forgot how we constructed it, but it looks like, yeah, we're getting a pencil of circles as well. Yeah, you can see the area is pretty close to -1. And then you get a similar phenomenon that we got before, which is, okay, let's move this guy inwards. So we got a change in topology, and then we got this isocurve, which is a straight line. So here we picked area equals 36. You can see that you're getting 36 there. Let's reduce the number of area samples so I can move this faster, like so. Okay. All right. Now what happens, so we get an idea of the topology of this thing, right? If I go here, okay, I immediately disconnect the two curves, and if I go here, I reconnect them, right? So they're connected. What if I go over here? Okay, they're disconnected. So there's some complexity to this, right, which is pretty interesting. You can see here that as, right, because N now has kind of a polarity, so if I'm up here versus I'm down here, things change a little bit, right? So it might not be so interesting to study this. We think that the highlight here is really what these isocurves of area are, okay? All right, so I'll see you on the next video.